All right, today we are going to pull back the curtain on one of the most famous promises in all of computer science. We're taking a journey deep inside the Java virtual machine to finally understand the magic that makes Java's whole philosophy work. Let's get right into it.
Write once, run anywhere. You've heard it a million times, right? For decades, this has been Java's battle cry. And let me tell you, this was a revolutionary idea. It completely changed how people built software, promising that you could write your code one time and it would just work on any machine, no matter the hardware or operating system.
But how? I mean, really, how is that even possible? How can you write a program on your Mac, and then your friend can run that exact same program on their Windows PC, and it'll also run on a giant Linux server in the cloud without changing a single line of code? Well, that's the puzzle we're going to solve today.
So, to understand this magic trick, we first need to get to know the magician's tools. And that means we've got to unpack a few of those famous acronyms that form the very foundation of the Java world.
You've probably seen these letters floating around: JDK, JRE, and JVM. The easiest way to think about them is like a set of Russian nesting dolls. The biggest doll, on the outside, is the JDK, the Java Development Kit. It's got everything a developer needs to build apps. Nestled inside that is the JRE, the Java Runtime environment. That's what you need to run the apps. And at the very heart of it all, the smallest doll is the engine itself, the JVM, the Java Virtual Machine. Let's try another analogy, because who doesn't love a good analogy? Think of the JDK as a fully stocked garage. It has all the wrenches, lifts, and tools you need to build a car from scratch. Now, the JRE, that's just the finished car. You don't need the garage anymore, you just need the car to go for a drive. But what actually makes the car go? The engine, of course, and that's the JVM. It's the powerhouse that actually does the work of executing your code. Okay, so if the JVM is our engine, let's do what any curious person would do. Let's pop the hood and see what's inside. Understanding its internal architecture is the absolute key to figuring out how this whole run anywhere thing is possible.
So when you look inside, it might seem really complex, but it actually boils down to three main parts. First, you've got the ClassLoader Subsystem. That's what brings your code into the machine. Then there are the runtime data areas. Think of this as the memory, where all your code and data live. And finally, the star of the show, the execution engine, which is what actually runs everything. Let's take a quick look at each one.
First up is the ClassLoader. Its job is to find your compiled code and load it into memory. And it's pretty smart about it. It does this lazily, which means it only bothers to load a piece of code the very first time it's actually needed. It's also super security conscious. It uses what's called a delegation model. Before it loads anything, it checks with its parent loader, and that one checks with its parent, all the way up. This simple chain of command prevents malicious code from tricking the system and pretending to be a core Java class. Next up, memory, or the runtime data areas. The two big ones you need to know about are the heap and the stacks. The heap is like a big, shared, communal playground where all the objects your application creates get to live. In contrast, every single thread of execution, every separate thing your program is doing at once, gets its own private stack. The stack is like a personal to-do list, keeping track of which methods are being called and what their local variables are. And that brings us to the final piece, the execution engine. This is where the rubber meets the road. Once the code is loaded into memory, the execution engine steps in to actually read the instructions and make things happen. But wait a second, what instructions is it reading? It's not the Java source code we wrote, and it's not the machine code that a specific computer understands. It's something else entirely. This right here is the secret sauce. This is the absolute core of the entire write once, run anywhere promise. The key is that the JVM doesn't run Java code. It runs a special, universal intermediate language that any JVM can understand. So a developer writes their human-readable code in a .java file. When they compile it, here's the twist. The compiler doesn't create a windows.exe file or a Mac application. Nope, it creates a .class file. And this file contains a universal set of instructions called bytecode. This bytecode is the blueprint, and it's designed so that any JVM on any operating system can read it perfectly.
So what does this universal blueprint actually look like? Well, to us humans, it's kind of gobbledygook. It's a structured stream of bytes. If you were to open one of these files, you just see a wall of this hexadecimal code. It looks like nonsense, but to a JVM, it's a perfectly clear set of instructions. And every single valid Java class file in the world starts in the exact same way. And this is the part I just love. Every valid .class file starts with these exact 4 bytes.
Cafe Babe. Seriously, it's known as the magic number. It's like a secret handshake. When the JVM opens a file and sees Cafe Babe at the very beginning, it instantly knows, okay, this is legit. I know what to do with it.
And right after that magic number, the rest of the file is this beautifully organized blueprint. It tells the JVM what version of Java it was compiled with. It has a constant pool that's basically a dictionary for the class. It has flags that say if the class is public or private. And of course, it contains the actual bytecode instructions for all the methods. It's totally self-contained.
Okay, so you might be thinking, hold on, reading and translating this universal bytecode one line at a time, that sounds slow. And you'd be right. The earliest versions of Java got a lot of criticism for being sluggish. The solution to this problem is one of the coolest pieces of tech in modern computing, the just-in-time compiler.
So the execution engine actually has two modes. It can be an interpreter, which is like a UN translator whispering in your ear, translating one instruction at a time. This gets the application up and running really fast. But for code that runs over and over again in a loop, it's not very efficient. That's where the just-in-time, or JIT, compiler comes in. The JIT is like a master translator who watches the code run, finds the most frequently used parts, and then compiles them on the fly into the super-fast native machine code for that specific computer. Modern JVMs do both, giving you the best of both worlds.
And the JIT compiler isn't just a simple compiler. It's a genius-level optimizer. It's constantly profiling your code to find the hotspots, the methods that are getting called all the time. It uses something called tiered compilation, where it starts with a quick and dirty compile, and then if a piece of code gets really hot, it recompiles it with a much more powerful optimizer for maximum speed. It even does clever tricks like method inlining, where it just copy-pastes the code from a small method right where it's being called to save the overhead of a function call. This is how Java can get performance that's right up there with languages like C++.
So let's put it all together. Let's trace the journey one last time. A developer writes .java source code. The Java-C compiler turns it into a universal .class file full of bytecode. That bytecode can be shipped to any machine in the world. The JVM on that machine loads it, starts interpreting it for a fast startup, and then the amazing JIT compiler kicks in, finds the hotspots, and transforms them into blazing fast native machine code. And that is how the promise is kept. And here's a final thought to leave you with. The JVM doesn't actually know or care about the Java language. It only cares about that bytecode format. This has turned it into this incredible polyglot platform, a home for all sorts of modern languages like Scala, Kotlin, and Groovy. So the real question for the future isn't just about Java anymore. It's, what's going to be the next great language to call the JVM home? Thanks for joining me.